Close your eyes and imagine yourself standing in a place where the night sky stretches endlessly above you. The air is crisp and clean, carrying the scent of snow and pine. Your breath forms small clouds that dissolve into the darkness, and you feel deliciously small beneath the vast canopy of stars. Here, in this perfect silence, you are about to witness one of nature's most extraordinary performances. Above your head, something magical is stirring. At first, you might notice only a faint shimmer, like moonlight reflected on water that isn't there. But as your eyes adjust to the darkness, this shimmer begins to reveal itself as something far more magnificent. Gentle ribbons of light start to unfurl across the sky, moving with the fluid grace of silk scarves caught in a cosmic breeze. This is Aurora, the northern lights, the southern lights, and tonight, you are going to understand the beautiful science that creates this celestial dance. You are about to discover that what appears to be pure magic is actually the result of an intricate conversation between Earth and space, a dialogue that has been happening for billions of years, long before humans existed to marvel at its beauty. The lights above you are not simply pretty decorations in the sky. They are the visible evidence of invisible forces at work, a gentle reminder that your planet is not isolated in the cold emptiness of space, but rather intimately connected to the Sun and the solar system in ways both subtle and profound. Every ribbon of green light, every curtain of purple fire, tells a story of energy and magnetism, of particles and atmosphere, of the delicate dance between destruction and protection that keeps life on Earth safe and thriving. As you watch the Aurora flow across the darkness like a river of light, you begin to understand that you are witnessing something ancient and ongoing. These same lights danced above the woolly mammoths and the first humans. They painted the sky for the dinosaurs, though no eyes then could appreciate their beauty. They have been Earth's constant companions through ice ages and warm periods, through the rise and fall of countless species. Through all the quiet moments and dramatic changes in our planet's long history, the Aurora moves in patterns that seem almost alive, pulsing and breathing with a rhythm that speaks to something deep in your imagination. Sometimes the lights hang, like curtains in a cosmic theater, gently swaying as if moved by an unfelt wind. Other times they spiral and twist, forming shapes that dissolve and reform in endless variation. Occasionally, they pulse with a heartbeat-like rhythm, growing bright and then fading, as if the sky itself is breathing. What creates this ethereal performance is a story that begins far from Earth, with the star that warms your days and lights your world. Your sun is not the calm, steady beacon it appears to be from your perspective. Instead, it is a roiling ball of nuclear fire, constantly exploding and reforming, sending invisible streams of particles racing outward through the solar system at incredible speeds. These particles, this solar wind, carry with them the energy and magnetism of the sun itself. When this solar wind reaches Earth, it encounters something remarkable: your planet's magnetic field, an invisible shield that extends far out into space. This magnetic field is generated deep within Earth's core, where molten iron swirls and churns, creating electrical currents that produce magnetism on a planetary scale. It is this magnetic field that makes Aurora possible, channeling the sun's energy into the precise locations where the lights can bloom. The meeting between solar wind and magnetic field happens hundreds of miles above your head, in regions of space where the air is so thin it barely exists. Here, in the upper reaches of Earth's atmosphere, particles from the sun collide with the gases that surround your planet. These collisions release energy in the form of light, creating the aurora that dances above you. But aurora is more than just a collision between particles. It is the visible manifestation of Earth's relationship with space, a reminder that your planet exists within a larger system of forces and influences. The lights tell you that Earth is not passive in its cosmic environment, but actively engaged, using its magnetic field to redirect and channel the sun's energy, transforming what could be harmful radiation into something beautiful and harmless. As you stand beneath the dancing lights, you realize that you are part of this cosmic conversation. The oxygen you breathe came from ancient stars. The calcium in your bones was forged in stellar explosions. The iron in your blood is the same iron that creates Earth's magnetic field, the same iron that helps generate the aurora above you. You are not separate from this dance of energy and magnetism. You are part of it, connected to the sun and the stars through the very atoms that make up your body. The aurora reminds you that science and wonder are not opposites, but partners, in helping you understand your place in the universe. Every green ribbon of light represents countless invisible particles finding their way through Earth's magnetic field. Every purple curtain speaks of atmospheric gases being gently energized by solar wind. Every pulse and shimmer tells the story of forces so vast and complex that it takes all of human knowledge to begin to understand them, yet so elegant and beautiful that a child can appreciate their magic. Tonight, as you prepare to explore the deeper mysteries of how aurora forms, you carry with you this sense of connection and wonder. The lights above you are created by the same star that will warm your face tomorrow morning, guided by the same magnetic field that protects you every moment of your life. You are about to discover how these invisible messengers from the sun begin their incredible journey across the solar system, carrying with them the energy that will eventually bloom into the fire in the sky above you. Your sun is not what it seems. From Earth, it appears as a calm, steady disk of golden light, rising and setting with reliable precision, warming your world with gentle consistency. But this peaceful appearance is an illusion created by distance and the protective veil of your atmosphere. The truth is far more dynamic, far more violent, and far more beautiful than this serene facade suggests. Right now, as you rest comfortably in the darkness, your star is engaged in a cosmic dance of destruction and creation that has continued for over 4 billion years. Deep in the sun's core, temperatures reach 15 million degrees Celsius, creating conditions so extreme that hydrogen atoms are forced to fuse together, forming helium and releasing enormous amounts of energy. This energy begins a journey that will take hundreds of thousands of years to reach the sun's surface, bouncing and ricocheting through the dense stellar interior like light trapped in a cosmic maze. When this energy finally reaches the sun's surface, it encounters a realm of magnetic fields and plasma storms that would dwarf any weather system on Earth. The sun's surface riots and convulses with magnetic activity, creating sunspots that are larger than entire planets, solar flares that release more energy than billions of nuclear weapons, and coronal mass ejections that hurl massive clouds of charged particles into space at speeds of several million kilometers per hour. It is from this chaotic, magnificent stellar atmosphere that the solar wind is born. Unlike the winds you know on Earth, which are simply moving air, the solar wind is a stream of charged particles, electrons and protons that have been stripped from their atoms by the sun's intense heat. These particles carry with them the sun's magnetic field, creating invisible threads of magnetism that stretch across the entire solar system. The solar wind flows outward from the sun in all directions, like an invisible river rushing through space. It moves at incredible speeds, typically around 400 to 800 kilometers per second, though during magnetic storms, it can move much faster. This means that particles leaving the sun today will reach Earth in just 2 to 4 days, carrying with them news of magnetic storms and solar activity that occurred on your star earlier this week. As the solar wind races through space, it encounters the planets of your solar system, each responding to this stellar breath in its own unique way. Mars, with its thin atmosphere and weak magnetic field, is stripped and scoured by the solar wind, slowly losing its atmospheric gases to space. Venus, shrouded in its thick, toxic atmosphere, creates a bow shock as the solar wind flows around it, like water around a stone in a stream. But Earth is different. Your planet has something that makes it special in the solar system: a strong, stable magnetic field that extends far out into space, creating a protective bubble called the magnetosphere. This invisible shield doesn't stop the solar wind entirely, But it does something far more elegant and beautiful. It redirects it, channels it, and transforms it into the raw material for Aurora. When the solar wind encounters Earth's magnetosphere, something remarkable happens. The streaming particles from the sun cannot simply push through this magnetic barrier, so they flow around it, compressing the magnetic field on the day side of Earth and stretching it into a long, comet-like tail on the night side. This interaction creates a complex, dynamic boundary where the solar wind and Earth's magnetic field engage in a delicate dance of attraction and repulsion. Some of the solar wind particles manage to slip past Earth's magnetic defenses, but not in the way you might expect. They don't crash directly into the atmosphere like cosmic bullets. Instead, they follow the invisible highways of Earth's magnetic field lines, converge and dive toward the planet's surface. Think of Earth's magnetic field as a vast, invisible funnel system, with the wide end facing space and the narrow ends pointing toward the magnetic poles, the charged particles from the solar wind. Follow these magnetic field lines, like cars following a highway, guided inexorably toward the polar regions, where they will eventually encounter the upper atmosphere and create the aurora you witnessed in the sky above you. This process is not random or chaotic, but follows precise physical laws that have been operating since the solar system formed. The stronger the solar wind, the more intense the aurora. The direction of the magnetic field carried by the solar wind determines how effectively it can connect with Earth's magnetic field. When the solar wind's magnetic field points south, opposite to Earth's magnetic field, the connection is strongest, and the most spectacular auroras result. The solar wind also carries with it the memory of the sun's magnetic activity. When solar flares erupt on the sun's surface, they accelerate particles to even higher speeds, creating shock waves in the solar wind that can trigger magnetic storms when they reach Earth. These storms can intensify aurora activity for days, causing the lights to appear at lower latitudes than usual, sometimes visible from locations that rarely see them. As you contemplate this invisible river flowing from your star, you begin to understand that the space between Earth and the sun is not empty at all, but filled with this constant stream of particles and magnetic fields. The solar wind is the medium through which your planet communicates with its star, the mechanism by which energy and information flow between the two bodies. The particles now spiraling down toward Earth's poles carry with them the signature of nuclear fusion from the sun's core, magnetic field information from the sun's surface, and the energy that will soon be transformed into the beautiful lights you see dancing in the night sky. They are messengers from a star, bringing news of magnetic storms and solar weather, carrying the raw materials that Earth's magnetic field will sculpt into rivers and curtains of light. These solar particles are approaching the final stage of their journey, descending along magnetic field lines toward the thin upper atmosphere, where they will encounter the gases that surround your planet. It is there, in the rarefied air dozens of miles above your head, that the invisible will become visible, the energy will become light, and the whispers from your star will bloom into the magnificent aurora that dances across the polar skies. But first, these solar messengers must pass through Earth's invisible guardian, the magnetic field that has protected your planet for billions of years, shaping and guiding their descent into the precise locations where aurora can form. Deep beneath your feet, nearly 3,000 kilometers below the surface where you rest, lies the beating heart of Earth's magnetic field. Here, in the planet's outer core, molten iron flows in vast currents, swirling and churning at temperatures that exceed the surface of the sun. This liquid metal ocean moves in patterns shaped by Earth's rotation, creating electrical currents that generate the magnetic field extending far out into space around you. You exist within this magnetic embrace without ever feeling its presence directly, yet it influences every moment of your life. This invisible shield has been protecting Earth for over 3 billion years, long before the first life emerged in ancient oceans, long before plants began producing the oxygen you breathe, long before any creature walked on land or flew through the air. It is one of the fundamental forces that made life on Earth possible, and it continues to safeguard your planet every second of every day. The magnetic field that surrounds Earth extends tens of thousands of kilometers into space, creating a protective bubble called the magnetosphere. If you could see this magnetic field, it would appear as a vast, teardrop-shaped cocoon surrounding your planet. On the side facing the Sun, the magnetosphere is compressed by the solar wind, creating a bow shock, where the streaming particles from your star first encounter Earth's magnetic defenses. On the night side, the magnetosphere stretches into a long tail that extends well beyond the Moon's orbit. This magnetic architecture is not static, but dynamic, constantly responding to changes in the solar wind and the Sun's magnetic activity. Like a living thing, the magnetosphere breathes and flexes, expanding and contracting as the pressure from the solar wind varies. During periods of intense solar activity, the magnetosphere can be compressed to less than half its normal size. During quiet periods, it expands gracefully outward, providing an even larger zone of protection around your planet. The strength of Earth's magnetic field varies across the planet's surface, but it is everywhere present, everywhere active. At the magnetic equator, the field lines run roughly parallel to the ground, creating a protective barrier that deflects most charged particles away from the atmosphere. But toward the poles, the field lines converge and dive steeply toward the surface, creating windows through which particles from space can descend into the upper atmosphere. These polar regions are where the aurora forms, where the invisible architecture of Earth's magnetic field becomes visible through the interaction with particles from the solar wind. The magnetic field lines act like invisible highways, guiding charged particles from space down into the atmosphere, precisely the right locations and the right altitudes to create the dancing lights you see in the polar skies. The magnetic field that creates these beautiful lights also protects you from dangers you never directly perceive. Without this invisible shield, the solar wind would gradually strip away Earth's atmosphere, just as it has done to Mars over billions of years. The charged particles from the Sun would bombard the surface, making it difficult for complex life to survive. The magnetic field deflects most of these particles, sending them harmlessly around the planet and out into space beyond but Earth's magnetic field does more than simply block harmful radiation. It also captures and stores energy from the solar wind, accumulating it in regions of the magnetosphere called the radiation belts. These belts, discovered in the 1950s by satellites, are zones where charged particles from space become trapped by Earth's magnetic field, spiraling back and forth between the northern and southern hemispheres along magnetic field lines. The radiation belts serve as a kind of energy reservoir for aurora activity. When the solar wind is particularly strong, or when the Sun's magnetic field connects favorably with Earth's magnetic field, energy can be released from these belts and channeled down into the atmosphere, creating the sudden brightening and movement that characterizes active aurora displays. Your planet's magnetic field is generated by the motion of molten iron in the outer core, but this motion is not random. It follows patterns influenced by Earth's rotation, creating a magnetic field that, like the planet itself, has north and south poles. However, these magnetic poles do not align exactly with Earth's geographic poles. The magnetic North Pole currently lies in the Canadian Arctic, several hundred kilometers from the geographic North Pole, and it moves continuously as the patterns of flow in the outer core evolve. This movement of the magnetic poles is part of a larger pattern of magnetic field variation that occurs over many different time scales. On short time scales of minutes to hours, the magnetic field responds to changes in the solar wind. On longer time scales of years to decades, the field reflects changes in the flow patterns deep within Earth's core. And on the longest time scales of hundreds of thousands of years, the magnetic field can actually reverse completely, with magnetic north becoming magnetic south and vice versa. These magnetic reversals have happened many times throughout Earth's history, recorded in ancient rocks that preserve the direction of the magnetic field at the time they formed. During a reversal, which can take several thousand years to complete, the magnetic field becomes weaker and more complex, with multiple north and south poles appearing at different locations around the planet. Aurora during these periods would appear at unusual latitudes and in unusual patterns, creating light shows unlike anything seen today. The magnetic field you live within is constantly interacting with the solar wind, creating a complex dance of forces that extends throughout the entire solar system. When the solar wind carries a magnetic field that opposes Earth's magnetic field, the two can connect and merge in a process called magnetic reconnection. This connection allows energy from the solar wind to flow directly into Earth's magnetosphere, powering the aurora and creating the spectacular displays that can be seen from space and from the ground. As you rest beneath the protection of this invisible shield, you can sense the profound interconnectedness of Earth's systems. The iron in your blood is related to the iron flowing in currents deep beneath you, generating the magnetic field that protects all life on the planet's surface. The oxygen you breathe exists because this magnetic field has protected Earth's atmosphere for billions of years, preventing it from being stripped away by the solar wind. The magnetic field that surrounds you is both ancient and immediate, both protective and creative. It has been shaping the interaction between Earth and space since the planet formed, and it continues to guide particles from the Sun into precisely the right locations to create the aurora that dances in the sky above the polar regions. It is the invisible conductor of a cosmic orchestra, directing the flow of energy and matter that creates the beautiful lights you see, painting the darkness with colors that have no earthly equivalent. Soon, you will discover what happens when the solar wind particles, guided by this magnetic field, finally encounter the thin gases of Earth's upper atmosphere, beginning the final transformation that turns invisible energy into visible light. 100 kilometers above your resting body, in the thin borderland between Earth and space, something extraordinary is about to happen. Here, where the atmosphere becomes so rarefied that molecules are separated by vast distances, the charged particles from your Sun are beginning their final descent along the invisible highways of Earth's magnetic field. This is the moment of meeting, the gentle collision that transforms invisible energy into the visible beauty of Aurora. The particles descending toward Earth are moving at incredible speeds, carrying with them the energy of your star and the memory of their journey. Across 93 million miles of space, they spiral down the magnetic field lines like invisible dancers following choreographed paths, their motion controlled by forces that have been shaping the interaction between planets and stars since the universe began. As these particles approach the upper atmosphere, they encounter the first wisps of air that still cling to your planet at this tremendous height. The atmosphere here is not like the thick, breathable air at the surface where you rest. Instead, it is a ghost of an atmosphere, so thin that a single breath at sea level contains more molecules than exist in several cubic meters of space at this altitude. Yet even this tenuous atmosphere is enough to create the conditions necessary for aurora. The particles from the solar wind, guided by Earth's magnetic field, begin to interact with the scattered atoms and molecules they encounter. These interactions happen on a scale so small that trillions of them must occur simultaneously to create even the faintest glow visible to your eyes. The process begins when a charged particle from the solar wind collides with an atom or molecule in the upper atmosphere. This collision doesn't destroy either particle, but it does transfer energy from the solar wind particle to the atmospheric gas. This transfer of energy excites the atmospheric atom, lifting one of its electrons to a higher energy level, like pushing a ball up a hill where it cannot remain for long. The excited atom exists in this higher energy state for only a fraction of a second before the electron falls back to its original level. When this happens, the excess energy must go somewhere, and that somewhere is into a photon of light. This single photon, invisible to your naked eye, carries the precise signature of the atmospheric gas that created it and the amount of energy that was transferred from the solar wind particle. Multiply this process by countless billions of interactions happening simultaneously across thousands of cubic kilometers of thin atmosphere. And you begin to understand how the aurora forms. Each individual collision creates a single flash of light, so brief and so dim that it would be impossible to detect. But when billions of these interactions occur together, they combine to create the flowing, dancing curtains of light that paint the polar skies. The location where these interactions occur is not random, but is precisely determined by the architecture of Earth's magnetic field. The field lines converge as they approach the magnetic poles, creating two oval-shaped regions around the north and south poles, where aurora most commonly appears. These auroral ovals expand and contract with changes in solar activity, sometimes growing so large that aurora can be seen from locations far from the poles, sometimes shrinking to small caps visible only from the highest latitudes. The altitude at which aurora forms is also determined by the energy of the incoming particles and the density of the atmosphere. The most energetic particles from the solar wind can penetrate deeper into the atmosphere before they lose their energy through collisions. Less energetic particles are stopped at higher altitudes where the atmosphere is thinner. This creates a layered structure to aurora displays, with different types of aurora forming at different heights above the ground. The most common aurora occurs between about 100 and 300 kilometers above Earth's surface, in a region of the atmosphere where oxygen atoms dominate. But aurora can extend much higher, sometimes reaching altitudes of over 1,000 kilometers, and can occasionally extend lower, down to about 80 kilometers above the ground during periods of intense solar activity. The interaction between solar wind particles and atmospheric gases is not a violent collision, but rather a gentle exchange of energy, like a cosmic conversation conducted in whispers. The particles from space do not destroy the atmospheric gases they encounter, but instead energize them temporarily, borrowing them for a moment as partners in the creation of light before moving on to interact with other atoms and molecules. This process is happening continuously above the polar regions, not just during visible aurora displays. Even when the sky appears dark and quiet, charged particles from the solar wind are constantly interacting with the upper atmosphere, creating a faint background glow that is too dim to see with the naked eye, but can be detected by sensitive instruments. The intensity of aurora depends on the strength of the solar wind and the efficiency with which Earth's magnetic field can channel the solar particles into the atmosphere. During periods of high solar activity, when the sun releases more particles and stronger magnetic fields, the aurora becomes brighter and more active. During quiet periods on the sun, the aurora fades to a gentle background glow, waiting for the next surge of activity from your star. The particles that create aurora do not come directly from the sun in a straight line, but follow complex paths through Earth's magnetosphere, sometimes spending hours or even days trapped in the radiation belts before being released into the atmosphere. This means that aurora activity can continue for several days after a solar storm, fed by particles that have been stored in Earth's magnetic field and are gradually being released. The beauty of this process lies not just in the visible result, but in the elegant physics that makes it possible. The same electromagnetic forces that govern the behavior of electrons in the atoms of your body also control the motion of particles in space and the emission of light in the aurora. The same quantum mechanical principles that determine how atoms absorb and emit light in a laboratory also operate in the thin atmosphere above the polar regions. As you contemplate this moment of meeting between solar wind and atmosphere, you realize that you are witnessing the visible manifestation of fundamental forces that operate throughout the universe. The light dancing in the sky above the poles is created by the same processes that make stars shine, that power the nuclear reactions in your sun, and that govern the behavior of matter and energy on every scale from the subatomic to the cosmic. The gentle collision between particles from space and gases in Earth's atmosphere creates more than just beautiful lights. It also creates a connection between you and the larger universe, a reminder that the boundary between Earth and space is not a hard edge, but a gradual transition where the terrestrial and the cosmic merge in a dance of energy and light. Soon, you will discover how the different gases in Earth's atmosphere each contribute their own unique colors to this cosmic dance, painting the night sky in hues that tell the story of the elements themselves. The air you breathe connects you to an invisible ocean that extends from the surface of Earth all the way to the edge of space. This ocean of atmosphere is not uniform, but layered, like a vertical landscape of different densities, temperatures, and compositions. Each layer has its own personality, its own role in the creation of Aurora, and its own contribution to the symphony of colors that dance across the polar skies. At the surface where you rest, the atmosphere is dense and rich, containing all the gases that make life possible. Nitrogen dominates, making up about 78% of the air around you. Oxygen comprises about 21%, the precious gas that fuels your body's metabolism and makes your existence possible. The remaining 1% consists of argon, carbon dioxide, and trace amounts of other gases, each playing important roles in Earth's atmospheric chemistry. As you rise through this atmospheric ocean, the character of the air changes dramatically. The first major layer, the troposphere, extends from the surface to about 10 kilometers above your head. This is where weather happens, where clouds form, where the air you breathe circulates in great patterns driven by the sun's heat and Earth's rotation. But this familiar realm of birds and airplanes is far below, where aurora forms. Above the troposphere lies the stratosphere, stretching from about 10 to 50 kilometers altitude. Here, the air becomes much thinner, and temperatures actually increase with altitude due to the absorption of ultraviolet light by ozone molecules. This ozone layer acts as Earth's natural sunscreen, protecting the surface from harmful radiation. The stratosphere is where high-altitude balloons float and where the fastest jets occasionally venture, but it is still too low for Aurora. Beyond the stratosphere lies a realm that most people never think about, but which plays a crucial role in Aurora formation, the mesosphere, extending from about 50 to 80 kilometers above the surface. The mesosphere is where the atmosphere becomes truly thin. Temperatures here drop to the coldest found anywhere in Earth's atmosphere, sometimes reaching -90 degrees Celsius. This is the layer where meteors burn up as they enter Earth's atmosphere, creating the shooting stars you sometimes see streaking across the night sky. But it is in the next layer, the thermosphere, where Aurora truly comes alive, beginning at about 80 kilometers and extending to over 500 kilometers altitude. The thermosphere is where the charged particles from the solar wind finally encounter enough atmospheric gases to create visible light, despite its name, which suggests heat. The thermosphere is a realm of extreme conditions that would seem both scorching and freezing at the same time. In the thermosphere, individual molecules are so energized by solar radiation that they move at tremendous speeds, corresponding to temperatures that can exceed 1,000 degrees Celsius. Yet if you could somehow survive in this environment, you would freeze instantly because there are so few molecules present that they could not transfer their heat to your body. This is a place where the normal rules of temperature and heat no longer apply in ways you can easily understand. The thermosphere is also where the distinction between different atmospheric layers begins to blur. Here, gases are not well mixed as they are in the lower atmosphere. Instead, lighter gases like hydrogen and helium become more dominant at higher altitudes, while heavier gases like oxygen and nitrogen become scarce. This separation by mass creates different zones within the thermosphere, each contributing its own characteristics to aurora formation. At the lowest levels of the thermosphere, around 80 to 100 kilometers altitude, nitrogen molecules still dominate, though they are present in much lower concentrations than at the surface. When charged particles from the solar wind excite these nitrogen molecules, they emit light in the red part of the spectrum, creating the rare red aurora but sometimes appears at the bottom edge of aurora displays during periods of intense solar activity. Higher in the thermosphere, between about 100 and 300 kilometers, atomic oxygen becomes the dominant source of aurora light. At these altitudes, the intense solar radiation has broken apart most oxygen molecules, leaving individual oxygen atoms scattered through the thin atmosphere. When these oxygen atoms are excited by particles from the solar wind, they emit the characteristic green light that forms the most common and recognizable aurora displays. Even higher, above about 300 kilometers, the atmosphere becomes dominated by lighter gases and by oxygen atoms in different energy states. Here, oxygen can emit red light, creating the red tops that sometimes crown tall aurora displays. The physics of light emission at these altitudes is subtly different from that at lower levels, involving longer-lived excited states that can persist for minutes before emitting their photons. The layered structure of the atmosphere means that aurora displays have their own vertical geography. A single aurora curtain can extend from about 100 kilometers to over 400 kilometers in altitude, with different colors dominating at different heights. From the ground, you see this vertical structure compressed into a two-dimensional display, but the aurora is actually a three-dimensional phenomenon with complex structure extending high into the thermosphere. The density variations in the thermosphere also affect how aurora develops and moves. At lower altitudes, where the atmosphere is slightly denser, aurora tends to be more stable and long-lasting. At higher altitudes, where the atmosphere is more tenuous, aurora can change rapidly, flickering and pulsing as the supply of particles from the solar wind varies. The thermosphere is also where Earth's atmosphere begins to interact more directly with space weather. Solar radiation and charged particles from the sun can heat the thermosphere, causing it to expand dramatically during periods of high solar activity. This expansion can affect satellites orbiting at these altitudes, increasing atmospheric drag and causing orbital decay. Understanding the layered structure of Earth's atmosphere helps explain why aurora appears where it does and why it has the characteristics you observe. The particles from the solar wind must penetrate deep enough into the atmosphere to encounter sufficient gas molecules for light emission, but not so deep that they are absorbed before they can create the sustained interactions necessary for visible aurora. The atmosphere's layers also act as a natural filter, separating the different types of particles from the solar wind based on their energy. The most energetic particles can penetrate deepest, reaching the lower thermosphere and mesosphere. Less energetic particles are stopped at higher altitudes, creating the layered color structure that characterizes many aurora displays. As you contemplate this vertical ocean of air extending above you, you begin to understand that aurora is not simply light in the sky, but a manifestation of the complex, layered structure of Earth's atmosphere. Each layer contributes its own character to the display, its own colors and behaviors determined by the specific gases present and the physical conditions at that altitude. The atmosphere that connects you to space is not empty space punctuated by occasional molecules, but a rich, complex environment where chemistry and physics create the conditions necessary for one of nature's most beautiful phenomena. Soon, you will explore how the specific atoms and molecules in this atmospheric ocean contribute their own unique signatures to the palette of colors that paint the aurora across the night sky. In the thin atmosphere above your sleeping form, a chemistry set more vast and elegant than any laboratory on Earth awaits the arrival of particles from the sun. Here, in the realm where atmosphere meets space, the same elements that fill your lungs and make up the air around you are transformed into something magical through interactions with energy from your star. This is where the familiar becomes extraordinary, where oxygen and nitrogen reveal hidden aspects of their nature that can only be expressed in the ethereal light of aurora. The oxygen you breathe at Earth's surface exists primarily as molecules too, oxygen atoms bound together in stable partnerships. But in the thin thermosphere where aurora forms, the intense solar radiation has broken most of these molecular bonds, leaving individual oxygen atoms floating freely through space. These single oxygen atoms, liberated from their molecular partners, behave very differently from the oxygen molecules you depend on for life. When a charged particle from the solar wind collides with one of these free oxygen atoms, it transfers energy that lifts an electron within the atom to a higher energy level. The oxygen atom now exists in what scientists call an excited state, carrying more energy than it can hold indefinitely. Like a ball balanced precariously at the top of a hill, this excited electron must eventually fall back to a lower energy level, and when it does, it releases the excess energy as a photon of light. The color of this light depends on precisely how much energy is involved in the transition. When an oxygen atom in the thermosphere releases its excess energy, it most commonly emits a photon in the green part of the spectrum, with a wavelength of about 558 nanometers. This specific shade of green has no equivalent in your earthly experience. It is a color that exists only in Aurora and in laboratory experiments that recreate the conditions of the upper atmosphere. This green light from excited oxygen atoms creates the most familiar and recognizable aurora displays, the flowing curtains and arcs that dance across the polar skies at altitudes between about 100 and 300 kilometers. The intensity of this green light depends on the density of oxygen atoms at these altitudes and the number of solar wind particles available to excite them. During active aurora displays, billions of oxygen atoms are simultaneously emitting green photons, creating the brilliant emerald curtains that can illuminate the landscape below. But oxygen atoms have more than one way to respond to excitation from solar wind particles. At higher altitudes in the thermosphere, around 300 to 400 kilometers above the surface, oxygen atoms can be excited to a different energy level that emits red light with a wavelength of about 630 nanometers. This red emission requires less dense atmospheric conditions than the green emission, which is why red aurora typically appears at the tops of aurora displays or during periods of very high solar activity, when particles can penetrate to higher altitudes. The red light from oxygen has a different character from the green. While the green emission is relatively quick, with excited atoms releasing their energy within about a second, the red emission can take much longer. Some excited oxygen atoms can remain in their higher energy state for several minutes before emitting their red photons. This means that red aurora can persist even after the supply of particles from the solar wind has diminished, creating a ghostly afterglow that slowly fades as the last excited atoms release their stored energy. Nitrogen, the most abundant gas in Earth's atmosphere, also contributes its own distinctive colors to the aurora palette. In the lower thermosphere and upper mesosphere, where nitrogen molecules still exist in significant numbers, these molecules can be excited by solar wind particles to emit light in the blue and purple parts of the spectrum. Nitrogen aurora is less common than oxygen aurora because it requires higher energy particles and specific atmospheric conditions, but when it occurs, it adds spectacular blue and purple hues to the display. The nitrogen molecules in the upper atmosphere can emit several different colors depending on how they are excited. Some transitions produce blue light around 470 nanometers, while others create purple and violet emissions. These colors often appear as fringes or bands within aurora displays, adding complexity and beauty to the predominantly green curtains created by oxygen atoms. The chemistry of aurora is not limited to simple emission of light by individual atoms and molecules. In the thin atmosphere of the thermosphere, chemical reactions that would be impossible at Earth's surface can occur. The high-energy environment created by solar wind particles can cause atoms and molecules to interact in unusual ways, creating excited molecular species that exist only briefly before breaking apart or emitting light. One of the most fascinating aspects of aurora chemistry is how it varies with altitude and atmospheric conditions. At the lowest altitudes, where aurora can form, around 80 to 100 kilometers, the atmosphere is still dense enough for more complex interactions between different gases. Here, energy can be transferred between different types of atoms and molecules, creating secondary emissions and affecting the overall color balance of the aurora display. The temperature in the thermosphere also plays a crucial role in aurora chemistry. The extreme temperatures at these altitudes affect how long atoms and molecules remain in their excited states and how efficiently they can emit light. During periods of high solar activity, the thermosphere can heat up dramatically, changing the chemical environment and affecting the appearance of aurora displays. The chemistry of aurora is also influenced by the seasonal variations in atmospheric composition. During winter months at the poles, changes in the thermosphere can affect the relative concentrations of different gases, subtly altering the colors and behavior of aurora displays. These seasonal variations add another layer of complexity to the already intricate chemistry occurring in the upper atmosphere. Understanding aurora chemistry reveals the profound connections between Earth and space. The same atoms that make up your body, that you breathe in with every breath, become the raw materials for one of nature's most spectacular displays when lifted to the thin atmosphere and energized by particles from the sun. The oxygen in your blood is the same element that paints green curtains across the polar skies. The nitrogen that makes up most of the air around you is the same gas that creates the blue and purple fringes in aurora displays. This chemistry occurs on a scale that defies easy comprehension. Each second during an active aurora display, trillions of atoms and molecules in the upper atmosphere are being excited by particles from the solar wind, each contributing its own photon to the collective glow that creates the visible aurora. The light you see represents the combined efforts of countless individual atoms, each following the same quantum mechanical rules that govern all matter in the universe. The colors of aurora are not arbitrary or random, but are the direct result of the fundamental properties of atoms and light. Each color tells a story about the specific gas that created it, the altitude at which the emission occurred, and the energy of the particle that caused the excitation. The aurora is nature's own spectroscope, revealing the composition and conditions of the upper atmosphere through the analysis of the light it produces. As you contemplate this invisible chemistry occurring high above you, you begin to understand that aurora is more than just a beautiful light show. It is a visible manifestation of the quantum mechanical processes that govern all matter, a demonstration of how energy and matter interact to create light, and a reminder that the same physical laws that operate in earthly laboratories also govern the behavior of gases in the thin atmosphere at the edge of space. Soon, you will explore how these different chemical processes combine to create the specific colors and patterns that characterize different types of aurora, and how the palette of the polar sky reflects the fundamental nature of the elements themselves. In the darkness above your resting form, nature has created the most ethereal art gallery in the universe. Here, suspended between Earth and space, colors bloom that have no earthly equivalent, hues so pure and luminous that they seem to belong more to dreams than to reality. Each shade in the aurora's palette tells a precise story about the invisible processes occurring in the thin atmosphere, revealing the secrets of atoms and energy through the universal language of light. The green that dominates most aurora displays is unlike any green you encounter in your daily life. It is not the green of leaves or grass, not the green of emeralds or jade, but something entirely unique, a color that exists only when oxygen atoms in the thermosphere release their excess energy after being excited by particles from the solar wind. This green has a wavelength of 557.7 nanometers, a measurement so precise it serves as a fingerprint for the specific energy transition occurring within oxygen atoms at altitudes between 100 and 300 kilometers above the surface. This aurora green appears so frequently because the conditions in the thermosphere are perfectly suited for its production. At these altitudes, oxygen atoms exist in abundance, liberated from their molecular bonds by intense solar radiation. The density is sufficient for frequent interactions with solar wind particles, yet thin enough that the excited atoms can emit their characteristic photons without interference. The result is the flowing, dancing curtains of emerald light that have captured human imagination for millennia. But the aurora's palette extends far beyond this signature green. Above the green curtains, where the atmosphere becomes even thinner and the oxygen atoms exist in a different energy environment, red light blooms with a haunting beauty. This red aurora, emitting at 630 nanometers, appears when oxygen atoms are excited to a higher energy level that requires different conditions to achieve. The red emission is more fragile than the green, appearing only during periods of high solar activity or at the very tops of tall aurora displays, where the atmosphere is tenuous enough for these specific energy transitions to occur. The red of aurora possesses an otherworldly quality that seems to glow from within. Unlike the quick emission of green light, red aurora can persist for minutes after an oxygen atom is excited, creating a ghostly afterglow that slowly fades as the stored energy is gradually released. This temporal characteristic gives red aurora a different personality from its green counterpart, more serene, more contemplative, like the last light of sunset captured and suspended in the night sky. At the lower edges of aurora displays, where the atmosphere is slightly denser and molecules have not yet been completely broken apart by solar radiation, nitrogen contributes its own distinctive colors to the cosmic palette. When nitrogen molecules are excited by high-energy particles from the solar wind, they emit light in the blue and purple portions of the spectrum, creating hues that range from deep violet to brilliant azure. These blue and purple emissions from nitrogen are less common than the oxygen colors because they require more energetic particles and specific atmospheric conditions. When they do appear, often as fringes or bands within predominantly green displays, they add a regal quality to the aurora, as if nature has decided to dress the night sky in royal colors. The blue light from nitrogen has a wavelength around 470 nanometers, while the purple emissions can vary in wavelength, creating a range of violet and magenta hues that shift and change as the atmospheric conditions evolve. The yellow-green that sometimes appears in aurora displays results from a combination of different emissions occurring simultaneously. When both the primary green line from oxygen and some of the blue emissions from nitrogen are present, they can blend to create a lime green or yellow-green color that adds warmth to the typically cool palette of aurora colors. This blending demonstrates how aurora colors can interact and combine, creating intermediate hues that reflect the complex chemistry occurring in the upper atmosphere. Occasionally, under very specific conditions, aurora can display colors that are extremely rare and special. Pink aurora can appear when red emissions from high-altitude oxygen blend with blue emissions from nitrogen, creating delicate rose-colored curtains that seem almost impossibly soft and beautiful. These pink displays are often associated with periods of intense solar activity, when particles with a wide range of energies are simultaneously exciting different gases at different altitudes. The intensity of aurora colors varies dramatically with the level of solar activity and the density of gases in the upper atmosphere. During quiet periods on the sun, aurora may appear as faint, ghostly green arcs that are barely visible to the naked eye. During periods of high solar activity, the same aurora can flare into brilliant displays where the green curtains are so bright they cast shadows on the snow below and the red tops glow like cosmic fire against the star-filled sky. The distribution of colors within an aurora display creates a vertical geography of light that reflects the layered structure of the atmosphere. Green typically dominates the lower portions of aurora curtains, where oxygen atoms are most abundant. Red appears at the tops, where the atmosphere is thinner and the conditions favor the higher energy oxygen transitions. Blue and purple from nitrogen, when present, often appear as lower fringes or as separate bands within the display. This color stratification means that the appearance of aurora changes depending on your viewing angle and location. An aurora display that appears predominantly green from one location might show prominent red features when viewed from a different angle or distance. The three-dimensional structure of aurora in the atmosphere creates a complex interplay of colors that can only be fully appreciated by understanding the physical processes that create each hue. The colors of aurora also change over time as the solar wind conditions vary and the atmospheric chemistry responds. A display might begin with faint green arcs, brighten into brilliant emerald curtains, develop red tops as the activity intensifies, and then fade back to a subtle green glow as the supply of particles from the solar wind diminishes. Watching these color changes is like observing a slow-motion fireworks display, where each hue represents a different type of energy interaction in the upper atmosphere. The purity of aurora colors results from their quantum mechanical origin. Unlike most earthly colors, which result from the absorption and reflection of white light by pigments and surfaces, aurora colors are created by individual atoms emitting specific wavelengths of light. This emission process produces colors of extraordinary purity and saturation, uncomplicated by the complex interactions that affect colors in the everyday world. The aurora palette represents one of the few ways that human eyes can directly observe quantum mechanical processes in action. Each photon of green light from an excited oxygen atom represents a single quantum transition, a discrete energy release that follows the fundamental rules governing how matter and energy interact throughout the universe. The colors dancing in the polar skies are visible proof of the quantum nature of reality, accessible to anyone willing to venture into the darkness and look up. As you contemplate this celestial color palette painting the night sky above the polar regions, you realize that you are witnessing one of the purest expressions of the fundamental forces that govern matter and energy in the universe. Each color tells a story, just of atmospheric chemistry, but of the quantum mechanical nature of atoms themselves, of the energy that flows from your star, and of the magnetic forces that guide particles through space to create this incomparable display of natural beauty. Soon, you will discover how these colors move and dance in patterns that reveal the dynamic relationship between Earth and the solar wind, creating rhythms and movements that speak to the fundamental harmonies of the cosmos. You are not the first to stand beneath these dancing lights, nor will you be the last. For as long as humans have lifted their eyes to the night sky, Aurora has been writing stories across the darkness, stories that have shaped cultures, inspired legends, and whispered ancient truths to those who knew how to listen. Imagine yourself standing beside a Norse warrior on a frozen fjord, watching ribbons of green fire unfurl across the star-scattered dome. To him, these lights are not particles and magnetic fields, but the gleaming armor of the Valkyries, warrior maidens riding their celestial horses across the bridge between worlds. He sees the aurora as a pathway for fallen heroes, their spirits, carried on waves of light to the great hall of Valhalla. The same photons that danced before you now once danced before him, carrying the weight of his beliefs, his hopes, his understanding of what it means to be human beneath an infinite sky. Move forward through time, and you find yourself beside an Inuit elder on the vast expanse of Arctic ice. She watches the same phenomenon, but her eyes hold different stories. To her people, the aurora is the dance of souls, the spirits of those who have passed on, playing an eternal game of ball with a walrus skull, their joyful movement creating these sweeping curtains of light. She tells you how the lights can be called down by whistling, how they respond to human presence, how they carry messages between the world of the living and the realm of ancestors. The science you understand mingles with her wisdom, creating something richer than either knowledge alone. But travel to the indigenous peoples of northern Finland, and you discover yet another layer of meaning woven into these same lights. The same speak of the aurora as the energies of the departed, but also as something more immediate, the reflection of flames from fires that warm the souls of those who have crossed over. They call it revanchulit, which means 5 forks flames, born from the tail of a magical Arctic fox running so fast across the snow that it kicks up a shower of sparks into the sky. Each flicker of light becomes a moment of connection between the earthbound and the eternal. But these are not merely quaint stories from a less scientific age. As you watch the Aurora pulse and flow above you, you begin to understand that these ancient peoples were seeing something true, something that transcends the boundaries between myth and measurement. They recognized that Aurora represents a bridge, a connection between visible and invisible worlds, between the familiar and the infinite. They intuited what you now know through science, that these lights are born from the marriage of earthly magnetism and cosmic energy, that they represent the planet's breathing, its conversation with the sun. The Aboriginal peoples of northern Canada saw the aurora as the dance of spirits, but they also understood it as a form of communication. They believed that clapping hands or making noise could make the lights dance more vibrantly, and modern research has actually found correlations between certain audio frequencies and aurora intensity. Their ancestors somehow sensed that these lights were responsive, interactive, alive in ways that Western science is only beginning to comprehend. In ancient China, astronomers recorded the aurora as dragon's breath or celestial energy. They understood it as a manifestation of Che, the vital force that flows through all things. When you consider that aurora is indeed the visible expression of energy flowing between sun and earth, between magnetosphere and atmosphere, their description becomes remarkably precise. They saw these lights as part of the same essential force that animates all life, connects all beings, creates the very breath you draw as you stand here now. Even the word aurora carries layers of story. The Romans named it for Aurora, goddess of the dawn, recognizing in these lights the same essential beauty that painted their morning skies. They understood that both dawn and aurora represented transitions, moments when the invisible becomes visible, when the ordinary world reveals its connection to something greater. They saw in both phenomena the daily reminder that light emerges from darkness, that beauty can appear in the most unexpected moments. As you stand here now, feeling the cold air fill your lungs, you are participating in this ancient human tradition of aurora watching. The lights that dance above you have danced above countless generations, each one finding their own meaning in the display, each one adding their own thread to the tapestry of human understanding. The photons entering your retina have traveled from the sun, interacted with Earth's magnetic field, excited atmospheric gases, and created the same spectacle that has moved hearts and minds for millennia. But you carry something unique to this moment in history. You understand both the science and the story, both the mechanism and the meaning. You know that these lights are created by solar wind particles following magnetic field lines, colliding with oxygen and nitrogen molecules, releasing energy as visible light. Yet you also feel the truth that your ancestors knew, that these lights represent something profound about the nature of existence itself, the way energy transforms, the way invisible forces become visible beauty, the way the cosmos expresses itself through phenomena that touch both mind and heart. The aurora connects you not just to the physical processes of space weather, but to the continuity of human wonder. Every person who has ever stood beneath these lights has felt what you feel now, the sense of being part of something larger than themselves, the recognition that beauty exists at scales beyond human making, the quiet awe that comes from witnessing the universe's capacity for surprise. Tonight, as these lights weave their ancient patterns above you, you become part of a story that began when the first human looked up and wondered. You carry forward the questions that have always driven human curiosity. What creates beauty? How are we connected to the cosmos? What does it mean to be conscious witnesses to the universe's magnificent displays? The aurora offers no simple answers, but it provides something better: a lived experience of mystery made visible, a reminder that the most profound truths often reveal themselves not through words, but through presence. through the simple act of standing still and allowing wonder to wash over you like these rivers of light flowing across the star-filled sky. Now, as your eyes begin to feel heavy and your breathing deepens, the aurora continues its silent performance. Above, this is perhaps the most beautiful truth of all, that the universe does not pause for human rest. While you prepare to surrender to sleep, the cosmos continues its ancient work, weaving patterns of energy and light that will dance through the darkness long after your consciousness fades into dreams. Feel how your body naturally begins to slow, your muscles releasing the day's tension as you settle into the rhythm of approaching sleep. Your heartbeat softens, your breathing becomes deeper and more regular, and yet above you, the aurora maintains its vigorous dance. Solar particles continue their 8-minute journey from the sun's surface, racing through the vacuum of space at speeds your sleeping mind cannot fully comprehend. They encounter Earth's magnetosphere, that invisible shield that protects you even as you rest, deflecting most of this cosmic wind, while allowing just enough through to create the lights that will continue their performance above your dreams. This is the magnificent paradox of existence, that rest and activity coexist, that your personal quiet does not diminish the universe's vitality. As your conscious mind prepares to step aside, allowing sleep to carry you into different realms of experience, the fundamental forces that create aurora continue their work with quiet persistence. Magnetic field lines stretch and reconnect, charged particles spiral along invisible pathways, atmospheric gases absorb energy and release it as photons that paint the sky in colors your dreaming eyes will not see, but your sleeping body will somehow still sense. There is something deeply comforting in this knowledge that the mechanisms of wonder do not depend on human witness. The aurora will dance whether you watch or sleep, whether you understand or simply feel. It represents the universe's generosity, its willingness to create beauty without audience, to maintain its magnificent processes, regardless of human attention. This is not indifference, but grace, the recognition that existence itself is valuable, that beauty serves purposes beyond human appreciation. What as you drift towards sleep, consider how your own body mirrors these cosmic processes. Your cells continue their work while you rest, repairing and renewing. Following ancient patterns coded in your DNA, your brain consolidates the day's experiences, weaving memories and insights into the neural networks that will wake refreshed. Tomorrow, your heart maintains its steady rhythm. Your lungs continue their exchange of oxygen and carbon dioxide. Your blood carries nutrients and energy to every corner of your being. You are, in your own way, as much a dancing system of energy as the aurora itself. The oxygen you breathe was once locked in ancient oceans, released by primitive algae, cycled through countless generations of living beings before finding its way to your lungs. The carbon in your cells was forged in the nuclear furnaces of dying stars, scattered through space, reformed into the building blocks of life. The aurora that glows above you and the consciousness that perceives it are both products of the same cosmic story, matter and energy arranged in patterns complex enough to generate beauty, awareness. Wonder. Sleep becomes not an escape from the universe, but a deeper participation in it. As your consciousness relaxes its grip on wakefulness, you join the great rhythms that govern all existence: the rotation of planets, the pulsing of stars, the slow dance of galaxies through expanding space. Your rest is not separate from cosmic activity, a part of it, a necessary pause in the endless conversation between energy and form, between potential and expression. The aurora teaches you that science and poetry are not opposites, but partners. In the same exploration, the equations that describe magnetic field interactions are themselves a form of poetry, compressed descriptions of relationships too beautiful and complex for ordinary language. The myths your ancestors created around these lights were their own form of science, attempts to understand and explain phenomena that exceeded their tools, but not their capacity for wonder. Tonight, as you surrender to sleep, you carry both forms of knowing with you. You understand the mechanisms that create these dancing lights, but you also feel their mystery. You know the physics of charged particles and atmospheric gases, but you also sense the deeper truth they represent, that the universe is fundamentally creative, fundamentally inclined toward beauty, fundamentally generous in its willingness to manifest wonder. Let your last conscious thoughts be of gratitude for the sun that provides the energy, for the earth that creates the magnetic field, for the atmosphere that transforms particles into light, for the human capacity to perceive and appreciate this cosmic artistry. As you drift into dreams, remember that you are not separate from any of this. You are made of star stuff, animated by the same forces that create Aurora, part of the same cosmic story that began with the first light in the universe and continues now in every photon that dances across the polar sky. The Aurora will continue long after you sleep, painting stories across the darkness, reminding any wakeful witness that the universe never stops creating, never stops surprising, never stops inviting us into deeper relationship with mystery. Even in your dreams, you remain connected to this vast, beautiful system of energy and form, consciousness and cosmos, sleeping and waking, all part of the same magnificent dance that needs no audience, but creates itself anyway, out of pure love, for the act of becoming. Close your eyes now, and let the Aurora dance through your dreams.